Yeah, I think it's just about giving a good presentation, not so much about fielding questions, right? Like, I don't think questions are serious. At least Roberto was like, oh, it's very much like, oh, what's another interesting application?
And he was also, Rohan was also saying like, make sure you only put stuff on the slides that you like
Trust.
really know well, because they're gonna ask like.
Yeah. I think I might not even talk so much about math, just talk about finance so that they can't ask any questions. Because I just have all these like really complicated. I'm like, I think I'm like four-fifths done. So, Roberto's like, oh, I think they extended the deadline. I was like,
And how was it due on the 10th? It's Friday. I thought Roberto was at 7:12.
this is but
So it doesn't matter what someone writes you says. The last 2 weeks, and I've been like going to it on like twice a week, and I'm just like stressed about it. And I don't know what to do. In May, I just.
May 12th at 5. I want to publish it. I'm trying to be done today, though. I have more. Not 34. This I haven't done. Any of these like 5, 7. I also
Oh, how much is it?
21, but I mean, mine was a full page. I haven't done photographs I want, and I haven't done introduction. It's also still called working title.
And I didn't know what to do with the slides on. He was like, Juan was like, they need to look polished, like they need to be absolutely, it's more important than anything.
I think I'm gonna go to take some screenshots.
That's what it was. It's gonna literally look so messy like that.
Background.
And he also was like, only like, he was like, 7 slides, like you need 20 that you can look at on your,
Right.
you look like you don't know it.
Yeah, you should get rid of your ideas. Not.
Ugh.
你别忘了今天最后一天去领开要在西楼圈领。如果你就是结束之后可以直接去领，然后再回来上课，或者是你可以课间那会儿去。
I think it do very large.
Okay, so it's about time to start our LSMAS. And again, reminder that we are going to read together, meet each other next Wednesday, but in the morning, at 9 a.m. Not between 9 a.m. and 11 a.m. I think is that the same place for the final? I can't exactly remember, but you should check it out. I'll also send another reminder to Rice Bus. Okay, today. So again, the coverage for the final is going to be chapter 4, chapter 5, chapter 6, chapter 7, and one question will come from chapter 12. Okay, and the amount of work is going to be slightly smaller than slightly less than Newton. So you will have more plenty of time. The difficulty roughly the same. And so it's mostly. I mean, you should not be worrying too much about that. Okay. And yeah, so this is everything that I have about final information about final. And but that doesn't mean that you don't have to. You don't need to. You don't need to review the first few chapters, because when they're referred to, they're referred to. I'm not going to design any problem that's, I mean, intentionally for chapter 1 to 3, but if the relevant knowledge is referred to, that should be referred to. Okay, so yeah, so I will be spending the yes.
And then question about the formulas and stuff. Okay,
so most of them will be given. most of them will be given, but if they are not given, that means that you're required to understand it, or at least know how to derive them in a very short time. Alright. So, so you know what? You don't need to worry too much about this because I plan to use the first hour to go through the rest of the things in chapter 12, and the next half hour or 40 minutes is going to be about. We are going to go through everything that we've learned from chapter 4 to chapter 12, and I'm going to comment on if you need to memorize anything or if you need to have the ability to derive the formulas in a very short time. Right? Okay. So so let's start from. So we have been talking about distribution, the idea of distributions. So one, we have been talking about distributions, and the idea of the distribution is that it is a mapping. It is a mapping always sending a function to a number. Okay? So distribution, the distribution D is always a mapping sending a function, for example L. Let's say L1 or L2 or LP, or so probably a less rigorous but more understandable way for D is that D is always sending some function fx, okay, to certain number A. Okay? So compared to the other relevant ideas, a function is something like, okay, so f is always sending a number to a number. Okay, here I'm just saying real number, but I'm not excluding complex functions, but we don't need to worry about it for now. Okay, and an operator, or sending A to B. Okay, an operator is always sending a function to another function. Okay? So as a comparison, distribution is neither. Okay? Distribution is something that's sending. Okay, is a mechanism that's sending a function to a number. Okay, and therefore the delta function is exactly a distribution that is always sending a phi x, okay, to phi 0, or it writes like delta phi x, the inner product between delta phi x equals to phi 0. So is it good? Okay, so this is the idea of distribution. And if a actually I should let's see. Actually, here I should replace the idea of a distribution to be functional, because distribution is actually linear and continuous function. So functional. Okay, delta is functional. And if a functional is both linear and continuous, then it's a distribution. So delta is also a distribution. Okay? Delta is also a distribution. The delta function is also a distribution. And the corresponding the corresponding examples that it actually includes, for example, we have been talking about several examples And let's see what examples that we have been talking about. So delta, okay, example number 1, that was delta. Okay, example number 2. Okay, example number 2. Okay, so for example, delta x minus 5, okay, is always sending, okay, so delta x minus 5 is always sending delta phi x, okay, to phi 5. Okay, so this is another example for a distribution. And or something like, okay, something like let's say, for example, let's say another distribution. So let's say I, okay, I is always sending phi x, okay, to its integration. Let's say the integration from negative infinity to positive infinity, okay, phi x dx. I is also a distribution. And we have been talking about the convergence of distribution. Which is that if I'm having a series of distribution starting from let's say f1, actually fn, okay? A series of distribution is converging to f, okay, actually converging weakly to f, okay, if and only if for any test function, okay, and we stress that the test function is actually an appropriate function, and we don't have to, actually we have no intention to get into very deep about what does it mean by an appropriate function. Just say it's a function that's not so bizarre. Okay, it's a function that's serving our purpose. So for any test function, phi fn, okay, the destination of fn sending phi is actually converging, when n goes to infinity, is converging to the destination of f sending phi. Then we're saying that fn is converging weakly, okay, to f. This is so-called the convergence of distribution. And based on that, we have discussed the example 4 and 5. We have been discussing the convergence. Okay, the convergence of, for example, first of all, for the diffusion. Sorry, for the source function of the diffusion process, Sxt, which is that Sxt satisfy that St equals to Sx, C, okay, something like, what symbol do we use? I think, let's just say C, okay, C, no, we didn't use C. What was the parameter that we used for a symbol that we used for the diffusion speed? Anyone remember? D, did I use D? Probably D, right? D, okay, Sxx, and Sx0 is exactly delta. Is actually delta function. Okay, this is the source function for the diffusion equation. Then we can say that, okay, Sxt, when t goes to 0, Sxt is converging to the delta function, okay, in a weakly fashion. This again is, we're talking about the convergence in the sense of weak convergence, and in the sense of the convergence of distribution. Because again, delta function, first of all, delta function is not a function, and therefore it's actually not a legitimate destination of convergence for a series of functions. So we can only discuss the convergence of Sxt when t goes to 0, okay, only in the sense of the distribution. Okay, and that actually means, okay, that actually is equivalent with the fact that from negative infinity to positive infinity as x t and phi x, okay, dx, okay, this is actually, when t goes to 0, this will actually converge to phi 0. Okay. This is the idea that the source function is converging weakly, okay, to the delta function. Okay, this is one thing. This is one example. And another example, this is actually, sorry, example number 4. And example number 5 was that the Dirichlet kernel, the Dirichlet kernel is exactly kn x equals to 1 plus 2, the sum m going from 1 to n cosine nx, okay? Which can be summed as sine m plus 1/2 x, okay, and over sine x over 2. And this Dirichlet kernel, because we have proved, that when n goes to infinity, okay, when n goes to infinity, the integration from negative pi to pi, kn x, okay, phi x dx, this will actually converge to 2 pi phi 0. Therefore, this is actually equivalent to that kn x is actually converging weakly, okay, to 2 pi delta x, okay, but this delta x is defined on negative pi to pi. Okay, this delta x is defined from negative pi to pi. Which means that this delta function actually, okay, which means that, let me stress again, the delta function over here, okay, the delta function over here, the delta function over here, they're two different things. Because one delta function is defined on the full, on the full real line, on the whole real line, which means that there is only singularity at one place, which is exactly 0. And the other one, the other delta function is defined on a periodic space from negative pi to pi, which means that if that delta function is extended to the whole real line, then this delta function will actually have a singularity for every pi, every 2 pi, for every 2 pi. Okay.
That's it.
Yes, go ahead.
We define the delta function to be the functional that assigns the number phi 0 to the function phi.
Yes.
And this operating is using convolution. Is it necessary using convolution?
No, we didn't. We actually did. Okay, so you probably missed the last class. So this is not a formal. What you have just said is a property of a delta function, but not a formal not a formal definition for a delta function. The formal definition of a delta function is here. The delta function is defined, okay, as a rule of mapping that always sending phi x to phi 0. That doesn't depend. That actually doesn't depend on anything about the convolution. The reason, the property that the convolution of delta function with any function is that function itself. Okay, is a property that belongs to the delta function, but it's not a formal definition of a delta function.
Then does this definition make delta unique?
Sorry.
Does this definition make delta unique?
In a weak sense, yes. Again, I cannot talk about I cannot exactly remember if we have gone through the idea about the functional. So function make up a linear space. Functional always also make up a linear space. That is called the dual space. Okay, in the functional analysis, that's called the dual space. Okay, of the function space. And the linear architecture. Sorry, the linear structure of the functional space and the linear structure of the function space. Actually, they have some relation, but actually not exactly the same. So when you are saying if that is unique, if that delta function is unique, then I can only say that when we are talking about the existence and uniqueness of the delta function, it relies on and only relies on the function space that you pick up. So to answer your question, does that make the delta function unique? I would say yes. Okay, yes, but weakly, because that means that we will be needing the test function or our function space, okay, to verify it. Okay, I hope this answers your question.
Can this be proved?
Sorry.
Can this uniqueness be proved?
Again, using the test function or using the linear structure of the function space that we concern, yes. Okay, which means that, or in another word, if we are looking into a completely different function space, then the idea of the delta function may actually be different. This actually this actually gives you a perfect example. The two delta x that we're talking about, they are because the first delta x is defined for functions defined on the whole real line. The second delta function is a functional, okay, defined for the functions defined only on between negative pi to pi. Okay. Therefore, although these two delta functions, they are written, okay, using exactly the same symbol, they are meaning two different things. Okay, they have different meanings. The first delta function, it only has one singularity as 0, and the second delta function, because first of all, the second delta function is only defined between negative pi to pi. Okay, it doesn't work. This delta function will never work. Okay, for a function that's not defined on the periodic space from negative pi to pi. But if we extend this delta function to the whole real line, then it will look like something that has a singularity for every 2 pi. I hope that answers the question. Okay, is that clear for everyone? I hope that discussion is also at least has intuitively clear. Okay, for everyone else. Okay, so yes, and the other example. Okay, the next example that we care about. Okay, the next example that we care about is actually the derivative. The derivative and integral of a distribution. Okay, the derivative and integral of a distribution. Well, that actually, first of all, it actually looks very anti-intuitive, right? Because, you see, we have stressed again and again that distribution is a functional, and a functional is not necessarily a function. Okay? Then, how can we possibly talk about the derivative and integration of a functional or a distribution? Okay? Because, for example, the delta function has a singularity. Everybody knows that if something has a singularity, then it's actually not differentiable, right? How can we possibly talk about the derivative or the integral of a distribution? Well, again, these things are defined in the weak sense. Again, if we are talking about the derivative and integral of the distribution itself, okay, that actually looks absurd. But if we are utilizing the derivative and integral of the test function to come back to define the derivative and distribution, the derivative and integral of the distribution, that will make sense. Okay? So for example, consider a distribution. Consider a distribution F. Okay? Consider a distribution F. Then the integral, the derivative of F, okay, is written as F prime. But again, F could just be singular, okay? And therefore we actually need to define F prime, okay, in the weak sense, or utilizing the derivative of test functions. So F prime is also, okay, f prime is also a distribution. Okay, the derivative of a distribution is still a distribution, just like the derivative of a function is still a function. Okay, so f prime is also a distribution, satisfying and satisfy that f prime, okay, f prime phi that equals to, okay, f prime phi that equals to negative f phi prime for any test function. Okay, for any test function phi x. Okay. Well, you might be very curious about why do we have the negative sign? Isn't that more natural? Okay, if we get rid of the negative sign and just say f prime is always sending the function f to the destination of f sending f prime. Okay, why would we need the negative sign over here? Well, the answer is the following. Okay, the answer is the following. Say this is because say f is also a C1 function, which means that if f is a first order differentiable function, okay, of course f doesn't have to be like that. But if f is a first order differentiable function, then what is f prime? What is the inner product between f prime and phi?
C1.
That's actually from integration from negative infinity to positive infinity. F prime x and phi x, okay, dx. This is inner product. Again, we're talking about inner product because this is the symbol of inner product. Okay, this is the symbol of inner product. And f prime, okay, the inner product between f prime and phi is going to be something like this. Right? Now, if we assume that both f prime and phi they are descending, okay, on the infinity, okay, quickly enough, which means that evaluating f prime infinity and f prime at negative infinity, evaluating phi at infinity and phi at negative infinity will be both 0. Okay? If we have something like that, then this guy will be something like, okay, so f prime, by doing integration by parts, this guy is going to be, okay, f x, okay, phi x, evaluated from negative infinity to positive infinity, and then minus from negative infinity to positive infinity, and then phi prime x, f x dx, using integration by parts, right? And this guy is going to be 0. This guy is going to be 0. If we assume that phi or f prime is descending, declining, okay, fast enough on both sides. Okay.
Professor.
So this is exactly and this is exactly what this is actually exactly negative. The inner product between f and phi.
那是，但是
Okay, this is exactly the inner product
比较别的是
between f and phi.
有别的有别的。
啊，没事，我一问，我一
F
问。
phi prime. Okay, so yes.
Professor, I have another question because it's not every functional can be written in the form of a function. So maybe we cannot write.
Sorry, can you say it again?
Is it that any functional can be written in the form of a function?
Yes, actually that's right.
How,
I mean, although sometimes we need some abuse of the integral notation, okay, but it is true that actually every distribution of function, okay, every distribution could be able to, okay, so the action of every distribution on a certain function could be always written into the inner product form or into the integral form. That is right. Okay, that's okay. And this is the this is f prime. Therefore, okay, therefore. So okay, so Therefore, there is an argument, okay, but we don't have time to prove that. There's an argument. Okay, so if Fn is converging weakly to F, then Fm prime is also converging weakly to F prime. Okay, Fm prime is also converging weakly to F prime. Okay? And again, as long as we are dealing with a nice set of test functions, as long as we're dealing with a appropriately defined function space. Again, I apologize for not saying this in a more direct way, but again, talking about this will be forcing us to get into the details of functional analysis. Okay, but we don't actually instead of getting very deep over here, actually the example in example 6a, okay, we'll be using the idea of a derivative of a functional, the derivative of a distribution to directly define what does it mean by the derivative of a delta function. Okay? The derivative of a delta function is that, okay, so first of all, the derivative of delta function is delta prime x. Okay, it writes like this. Okay, can anyone guess what's the rule for delta prime? Delta is always sending phi to phi 0. So we would imagine delta prime is always sending phi x to what? To negative phi prime 0, right? To negative phi prime 0. So delta prime x is also a distribution sending phi x to negative phi prime 0, or more mathematically writing, it looks like, okay, delta prime phi, okay, equals to negative delta phi prime equals to negative phi prime 0. Okay, same reason, we will be able to define what is meant by delta. Well, what is meant by phi delta prime prime? Okay, delta prime prime phi should be what? Delta prime is a distribution. Okay, this is the first order derivative of delta function. What does it mean by the second order derivative of delta function? The first order derivative is sending phi to negative phi prime 0. So the second order derivative should be sending phi to what?
Phi prime prime.
Okay, negative or positive?
Positive.
Positive, because negative and negative, right? Negative for one time, negative for another time should be sending phi to phi prime 0. Okay, how do we see that? We can see that actually this will look like, okay, negative phi prime, delta prime, phi prime, which is positive, okay, delta phi prime, which is phi prime 0. So that's good. And so of course you will be able to define any order of derivatives, okay, for the delta function. Any order of derivatives for the delta function. Okay. Well, integration. 7. Okay, integration. In the integration of a distribution, okay, the integration of a distribution, it will actually looks like that. Okay, it will actually looks like that. See, so sorry. So that means that let's consider a distribution f, okay? Then its integration f, the big F, should satisfy that f is also a distribution, okay? as long as it satisfies that it's sending the functions to finite numbers. Okay? F is also a distribution, and F, okay, F phi, well, it's actually the integration, okay, of F and then phi, and it can actually be represented as F and the integration of phi. Okay, F and the integration of phi. Or how do you see that? The way to see that is something like, okay, so if I'm having a distribution, if I'm having a distribution F, okay, if I'm having a distribution F, then again, consider that F is an integrable function, okay? If F is consider if F is an integrable function, if F is an integral function, then let's say, then F phi, it actually looks like the integration from negative infinity to positive infinity, right? And F x phi x dx. So far so good? So far so good? And by the integration by parts, okay, by doing integration by parts, it actually equals to F, okay, it actually equals to F x phi x evaluated from negative infinity to positive infinity. So far so good? So far so good? And then minus the integration from negative infinity to positive infinity is going to be fx, okay, and then db phi x, where here phi x is exactly the integration from negative infinity to x, okay, phi y dy. So that's good. This is done by integration. This is done by integration by parts. And then one more step, okay. Wait a minute.
I think it's
Sorry.
negative.
Sorry. No, this is wrong. Okay. So this is the second step. Sorry. Here, this is the second step, and let me. Here. Okay. This is good. And this will actually equals to. Let me see. So did I make a actually? So I think I have also made a mistake over here, right? Here it actually should be fx. Sorry. Yes. Which equals to equals to fx, and then phi x, big phi x, evaluated from negative infinity to positive infinity, and then minus the integration from negative infinity to positive infinity, big phi x, and then d fx. Well, d fx is exactly fx dx.
So it should be negative.
Okay, which means that this is exactly okay, big phi and then f. Sorry. F and then negative f and then big phi. Again, this is based on if we assume that both fx and phi x they are declining fast enough. Okay? If they are declining fast enough, or at least one of them is declining fast enough, okay, on the both sides, then we'll be able to ignore this. Okay, but so what type of function could have such a property? That usually means that my phi x, okay, the test function space phi x, okay, it is declining fast enough. And therefore, by the same definition, okay, example 7a, by the same definition, 7a, we are able to talk about the integration of delta function. What is the integration of a delta function? What is the integration of a delta function? We have learned that previously in the section of diffusion equation. Right? What is the integration of a delta function? Heaviside function. One is actually a Heaviside step function. But how do we see that? How do we see that? So that means that, okay, that means that the so how do we see that? Okay, this actually can be seen in the sense that, okay, so Heaviside function hx, which is defined as 1 for x to be larger or equal to 0 and 0 for x to be smaller than 0. So actually this can be seen as that h prime phi, okay, h prime phi actually equals to negative h phi prime, okay, and which equals to negative the integration from negative infinity to positive infinity hx, okay, and then phi prime x, and then dx, which equals to the integration from 0 to infinity, because this is because h is only positive, is only non-zero, okay, when x is larger or equals to 0. So this will actually equals to the integration of phi prime x, okay, dx, from 0 to infinity, which equals to negative, okay, phi x evaluated from infinity to 0, okay, and which is phi 0, which is phi 0. Therefore, okay, we can say that h prime equals to delta function. H prime is the delta function. Okay. And that's okay. Now, having those things in mind, now we are able to proceed, okay, to example number 8. We're able to proceed to example number 8. So the first thing I would like you to do is to take some time, okay, to compute a Fourier, actually 3 different Fourier series. Okay, 3 different Fourier series. So, well, actually, yes, 3 different Fourier series. I would like you to compute the full Fourier series, okay, for x, okay, the absolute value of x, and the Heaviside function hx, okay, and well, okay, you don't have to compute the Fourier series for delta x, because we already know that delta x equals to we have already known that delta x equals to let me see, the sum, okay, sum from okay, which n is odd, 2 over pi, okay, 2 over pi cosine nx. We already know this is the Fourier transform for delta x. But I would like to ask you, okay, to compute the Fourier series for absolute value of x and hx. Okay, let's do that. Okay, again, the full Fourier series for these functions for x between negative pi to pi. I think this is also a very good chance for us to do some review. Can you please do that? Pull out some piece of paper. is one of it. Okay, anyone ready to present for the Fourier transform or absolute value of x, or the Fourier series, or absolute value of x, or the Fourier series for Heaviside function? Anyone ready to present that? But probably going to have another 2 minutes for that, right? agree? Present something?
到底是什么意思？
So better be more familiar with this, right? Because this is actually very likely to be part of your final.
I can present the absolute value.
Sure, yes, go ahead.
A little further on.
Why don't you explain?
Sure, yeah, yeah, you just act as if you were.
So I can use the formula for this like the minus pi to pi. And I write this formula of this should be a n cosine nx plus b n sine nx. And since this is an even function, so we can find out this is zero since
Sure.
it's even.
Because it's even, so we don't need a sign, we just need a sign false.
The formula for a n equals to 1 over pi minus pi to pi. And here should be the absolute value of x cosine nx dx. And then the thing inside is also even, so we can erase this to 0 and add 2 here. So this comes and the absolute value disappears, so this comes to 2 over pi. 0 to pi x cosine x, and use integration by parts to get this equals to x over n cosine nx. Evaluate at x equals to 0 to pi minus integral of 0 to pi sine nx over n.
You integration by parts, should that be cosine nx, or I mean the first term, should it be cosine nx or sine nx?
Or sine of nx.
I mean, and the first term is.
Sine. Then this is just 0 because sine and pi and sine 0 are opposite. So then we got minus 2 over pi n minus integral even this equals to 0. So we only have when n is odd. We have this equals to get to the negative, so this is -4 over n squared pi.
That's
the
what we
form
have.
of the book.
Okay, thank you. Any question for this? No? Okay. Okay, what about the second, what about the other one, HX? Does anyone would like to contribute for HX? Okay, we have plenty of time for this. How should I wait for everyone to
它第一个有加1/2吗？就是 x 的绝对值那个，它需要加上一个就是 1/2。
你说 a0吗
对对对，
？a0要加，
是1/2。
如果是按照那个公式就加。
这个和那个电脑一样的问题是，它现在
那你要是他求导也是看吧。平时你像他白菜。他白菜你求他。他这个就真是可能。
So, another way to proceed with the HX, well, because HX is neither odd nor even, right? So that's actually may take you a little bit more time. But one way to see this is actually, you see, HX is what? HX is a Heaviside function going from 0 to 1, right?
-1.
If you double it, it should now go from 0 to 2. Right? This is HX. This is 2HX. So good? Okay. Then what if I minus HX, the 2HX by 1? Then 2HX minus 1 is going to be something like this. This is 2HX minus 1. Now this function is what kind of function? Now it's odd. Okay. Now you can proceed with only having the sine terms. Okay. Only having the sine terms. And actually, thanks to Rong Yao, and we are having what we are having for the Fourier series. Okay, for the Fourier series for the absolute value of x is actually pi over 2, and then minus the sum when n is odd, and 4 over m squared pi cosine nx. Okay, and for hx, okay. So for this, for 2hx minus 1, if you do the Fourier transform, for the Fourier series, for 2hx minus 1, then what you would obtain is going to be something like, the sum when n is odd, sine nx, and then 4 over m pi, okay? So what relation do you see between these two terms? You see, what is hx? What is the absolute value of x? the absolute value of x is something like this, right? What is the first order derivative of the absolute value of x? What is the first order derivative of absolute value of x?
Minus 1 minus 1.
Okay, so this guy taking the first order derivative is going to be something like this.
Oh,
Right? This is what? This is exactly 2hx minus 1.
Oh.
Right? 2hx minus 1 is exactly the derivative of the absolute value of x. Well, what about looking into the Fourier series? We said that when we are doing the Fourier series, we cannot differentiate term by term, right? We stress this point. We cannot differentiate term by term because we cannot guarantee the convergence. However, when we are actually, what will you find that? But again, I don't have time to explain why is that. But if we are talking about the differentiation, okay, of distributions, when we are accepting that the absolute value of x, hx, delta x, when they are distributions, then you see now if I take the derivative term by term, the derivative of pi over 2, of course, is 0. The derivative of every single term over here, well, cosine x, take the derivative, is going to be n sine nx. And what negative n sine nx, so negative sine becomes positive sine. And one over n squared is going to become 1 over n. So this is actually the derivative of this term by term. So is it good? Okay. And so here we can say that hx is what? Hx is what? Hx is actually, okay, 1 over 2. So if I am putting the 1 to the right hand side, okay, and then divide both sides by 2, then we will have 1 over 2, hx equals to 1 over 2, and then plus sum when n is odd, okay, 2 over n pi sine nx, right? So far so good? Well, what we just say for delta x? Delta x is exactly the sum where n is odd, okay, 2 over pi cosine nx. See? Okay, again, if I'm taking derivatives term by term, I arrive at a Fourier transform. Okay, a Fourier synthesis for delta x. Okay, so that's good. Okay, so this is probably everything that we have for, let's see. Yeah, okay. For 12.1. Okay. One would take a 5 minutes break, and then we'll come back. Talking about something about 12.2, and then we'll come back for a brief review.
哦，现在这是这样子。哦，就你刚才提的是在等下去 x， 你是将 x 乘上。哦，比如说乘上一个 x。
Yes, go ahead.
Does it matter that the value of x doesn't have a derivative?
See, that's exactly what we were talking about. That's exactly what we're saying. That you see, here we are talking about derivative in the sense of distribution. Therefore, we carry out the derivatives.
Okay.
If you are still taking absolute distribution as a normal function, then you will do that. Because you cannot guarantee convergence.
是我们看出来的，是我们知道的，这不是根据这个公式得出来的。
但是你说这个人的这代表说这公司要废了，然后那不是他还招新人？
啊，对啊。
就是你知道吗？现在我们好多人聊很多好处，就是说有学校跳楼的打人，还是健身。然后我今天跟教授谈了，我跟你说，这个算数。我第一个我少乘了一个2，第二个我多乘了一个2，我觉得我考试要废了，真的。
那这种weak
对，考试完后，但是你说我5x4，你这是一个议论方程对吧？然后乘2就是你取掉，后面那个没怎么算出来，然后前面那个2就忘了，我去，我真的是急。
是。
就是weak
就是说，这整个如果都是建立在weak convergence 上，首先为什么左边的这玩意儿就可以 differentiate term by term，以及右边的这个玩意
现在有这个 f 分考完就把它统一，
对，
所以 f prime 到 f prime 为weak。
那 f prime
那你现在绝对是 f 4。
我们就认为绝对是 f 的 prime 是这个。
啊，对啊。
那右边的这个玩意儿的 prime 是为什么一定是这个？
啊，term by term
为什么可以 term by term？
因为我现在 term by term 完了，它不就是 f 吗？term by term 不是 f prime。
不是，就是 f
那我现在就能说明它考
不，我的意思是说，就是说 Fourier series 不一定能 differentiate term by term。那我们这里的这个 derivative， 这里的 derivative 也是 define
Fourier series 只是 term by term 不一定 convergence。你任何东西都可以 term by term differentiate。现在就确保了 term by term differentiate 这样是 convergence。
那但是可是我们的这个 derivative 这里讲的，如果我再把它看成 distribution 的话，它的 derivative 是定义在 inner product 上，它包含了我们传统意义上的 derivative。就是我的意思是，如果我们既然用 weak convergence 的话，那我们也得同样的用。
哦，对啊。不是，你只要满足这个性质就可以。
只要满足这个性质。
只要满足这个性质，就是 f prime 是 f 的 derivative。
OK，所以说我们是不是其实还得验证一下这个玩意儿做积分之后？